Welcome to the video on the common ion effect. This is a lot like Le Chatelier for acids and bases. Basically, the idea is if we have this acid dissociation equation, it doesn't matter whether it's acetate or whatever, but we have acetic acid will dissociate and create hydrogen ion and acetate ion. Any acetate ion containing chemical that we add to this will, because of Le Chatelier, shift this equilibrium to the left. So if we add anything here, like sodium acetate or potassium acetate, it doesn't matter what the cation is, it's just that it's adding the anion base there. That will shift the equilibrium to the left, because we know that if we add something to one side of the equilibrium according to Le Chatelier, it'll shift away from it. So it'll go back to making more of the acetic acid. As it shifts to the left, the amount of hydrogen ion will be decreasing because it's shifting away from hydrogen ion. So therefore, the pH will also will increase. Because if your amount of hydrogen ion is decreasing, you're becoming less acidic, so you're becoming more basic, so your pH is going up. So when it comes to acids and bases, Le Chatelier is going to have an effect on pH, because if you shift your equilibrium one way or the other, you're going to change how much hydrogen ion you have. Or it also works just for hydroxide ion. So let's say that we have the base dissociation equation for ammonia, and it creates ammonium ion and hydroxide ion. If we add something that contains ammonium ion, so ammonium chloride or ammonium, let's say oxide, it doesn't matter. Whatever, if it contains this ion and it's an ionic compound, then it's again going to shift to the left, which will decrease the amount of hydrogen we have, and hydroxide we have, and so that it becomes less basic or more acidic, so therefore our pH will also go down, become more acidic. So let's try some practice problems with this. What does this essentially mean as far as when we're calculating with rice tables? This means that instead of what we're used to doing is saying, it's not a very good marker, but we'll have an initial for one of these and then 0 for the two products. Now we're actually going to have a value for our products. So let's try this practice problem here. Let me get a better marker. Okay. So we want to know the pH of a solution, so we're going to look for pH, and hopefully that rings a bell in your head that says I need to find hydrogen ion concentration so that I can put it in the pH formula. So that's our goal. We have a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate. We don't care about the sodium, but we care about the acetate. 2 enough water to make 1 liter. Well, that was nice of them, because then our moles is the same thing as our molarity. So we're going to need a rice table, and acetic acid is going to make hydrogen ions and acetate ions. Okay, we're starting with 0.3 molar of the acetic acid, and we're starting with 0.3 molars of our acetate. Again, we don't care about the fact that the sodium acetate is not. We have none of this. Okay, so then the question is, what's going to be my pH? Well, I'm going to need some of this hydrogen ions. So we're like, okay, well, we know that if we only have something here, we have 0 here, we have 0 here, then we're going to lose some amount here, and we're going to gain it over there. But what if we have something here and something here? We still are going to go in this direction and lose here to gain here, because we have nothing of this. We can't lose this. Because in order for this to go down, we have to add a hydrogen ion to it to get it to go back here. We have no hydrogen ion to add to it. So we have to still be losing here, gaining here. So we're going to be losing X and gaining X. So our equilibrium concentration, 0.3 minus X, X is 0.3 plus X. So then we're going to need to know the Ka for acetic acid. The Ka for acetic acid, if we look at our appendix D, is 1.8 times 10 to the 5th. And so we write our Ka expression, hydrogen ion, products over reactants, Ka we said was 1.8 times 10 to the negative 5 for acetic acid. Now, this is x. This is 0.3 plus x. But remember, we can get rid of plus x and minus x. So far, we've never had plus x to get rid of, but it works just the same way as getting rid of the minus x. So we have x times 0.3, get rid of that minus x, divided by 0.3, get rid of the minus x, equals that. Well, the 0.2 is going to cancel out, so how convenient is this? So then x equals 1.8 times 10 to the negative 5. Every time you solve and you find what x is, you have to remember, what does x stand for? In this case, x stands for the hydrogen ion concentration. How convenient. We want pH, so therefore we have to take the negative log of this, and the negative log will give us 4.74. So that's our answer for this question. Now, in this case, the 0.3 is canceled out. It won't always be that easy. If you have different numbers here, you're not going to cancel out, and you'll actually have to do the math. But let's try another problem. Okay, calculate fluoride ion concentration and pH. Okay, so we got two things to do here. Let's see if I can get another marker. We need the fluoride ion concentration. What does that mean? That means something looks like this. And pH of a solution containing 0.1 moles hydrochloric acid and 0.2 moles hydrofluoric acid in a 1 liter solution. All right, so we have our hydrofluoric acid. That's our weak acid. So when we do a rice table, we're going to put the hydrofluoric acid in there. We're not going to put this in here because this is strong acid. We don't use that in rice tables. So we have hydrofluoric acid. Splits into hydrogen and fluoride ions. Aha, that's the thing we're trying to solve for. And let's put our numbers in here. Well, this one's easy. We have 0.2 moles of hydrofluoric acid. Again, they gave us 1 liter. How nice of them. So 0.2 moles is 0.2 molarity. And then, what's this? Where are we going to put this? Well, we can't put it here. We already put something there. There's no fluorine in it, so it's clearly not going to go there. But this is a strong acid. Remember, the concentration of a strong acid is equal to the concentration of the hydrogen ions. So who cares about this chloride? We are just going to use this number as our hydrogen ion. And we don't have any of that to start with. Again, because there's 0 is on our product side, we're going to lose reactants. We're going to gain products. 0.2 minus x, 1 plus x, and x there. All right, again, we're going to need to know what our Ka is. We need to write our Ka expression. So we have hydrogen ion, fluoride ion, divided by hydrofluoric acid. And the Ka for hydrofluoric acid is 6.8 times 10 to the negative 4. And that's going to equal, we're going to get rid of our plus x. So 0.1 times x, there's a 0.1 into x, get rid of the plus x. We're going to get rid of our minus x there, 0.2. Now, you're saying, wait, time out. You told us that we can only get rid of plus x and minus x when this number is less than 1 times 10 to the negative 4. This is more than 1 times 10 to the negative 4. Do we have to use a quadratic equation? The answer is no, because it's a common ion effect. Because of this amount of hydrogen here, this x is going to be less than it would have been if there wasn't any here. If we start off with 0 here, then we're going to be dissociating more of the hydrofluoric acid to create more of our products. But because this is already here, this x is not going to be quite as much. We're not going to dissociate as much of our hydrofluoric acid, so we can, in fact, get rid of our plus x and minus x because it'll still be less than 5%. This number will be less than 5% of this number. Watch and see. All right, so now we have to solve this. So we multiply by 0.2, we divide by 0.1, and x equals 1.4 times 10 to the negative 3. Okay, again, what is x? Don't jump right into the whole x is our hydrogen ion concentration, because that's not true. X is our fluoride ion concentration. Well, that's great, because that's one of the answers that we wanted. Okay? But the other one is pH. Well, in order to find pH, we have to know our hydrogen ion concentration. Well, 0.1 minus 0.0014. If we round to sig figs, it's still pretty much 0.1. So our hydrogen ion concentration, our pH, is going to be based on our strong acid, not our weak acid. That makes a lot of sense. So our pH is going to be the negative log of our strong acid. those situations. All right, so there's two examples of common ion effect, and we'll do a few more in class. Thank you.